Okay, in this video, there is a lot to unpack. And if you're a student currently taking a logic class and you have reached the portion where you talk about sound arguments and complete arguments, but you're not really understanding what any of it means, then I would highly encourage you to watch the entirety of this video because I'm going to do my best to explain these concepts to you because I understand that they're difficult to understand and put them in practice, hopefully, in a way that will make them easier to understand. So, I know I said countermodel on the top of this, but first I just want to talk about validity. We have two notions of validity, semantic and proof theoretic kind of way. So what do I mean by that? Well, we have done the Tableau model, right? The tree. And we've written out some set of premises and a conclusion, and then we put a weird little symbol in between them, right? This was the symbol that we used so far. Let's make sure I have the right pen selected. So we used this symbol. And that's what we use for our proof theoretic validity. So validity is kind of defined in terms of some formal procedure. And in our case, the procedure we've been doing is the tree diagram. So if I have some set of premises, we'll call them sigma, right? And we'll use a capital sigma just to represent all premises because I don't want to write them all out. So as we've shown with our tree diagram, right? If we do our tree and we have our set of premises and then negate the conclusion and it all closes, we've seen that the set of premises sigma semantically entails, and then let A be our conclusion, A. So that's something we have seen. So sigma syntactically entails A if and only if the tree for sigma not A, right? Because that's what we've been doing is we've been negating our conclusion, closes. So that is one model of validity. Another is the semantic version where we say that every interpretation makes the premises true, makes the conclusion true. So here I'm going to introduce a new symbol. We'll say sigma. Again, this is the set of our premises. Semantically entails A. So it looks like a sideways pie, but it looks like our syntactically entails symbol just with another arm sticking out. So sigma semantically entails A if and only if there is no interpretation, or maybe I should say valuation. Let's say there is no valuation V. There is no valuation V such that V of sigma, and this loosely means that here, let me write this out. V of sigma equals 1, and V of A equals 0. So what does that actually mean? Well, the 1 means true, and the 0 means false. So I'm saying sigma will semantically entail our conclusion A, if and only if there is no valuation V that makes the premises true and the conclusion false. Now, we've never talked about valuations before, so this is a good time to talk about them. Basically, how we're going to do valuations, right, is if we have a tree and it does not close, and we have an open branch, right? What we do is we assign values 1 or 0, meaning true or false, respectively, to each parameter based on how they are on the tree. So if P shows up on a tree, on a branch, that will equal 1. V of not P is equal to 0. And these are just numbers, but again, they correspond to truth values, 1 true, 0 false. So let's say I wanted to know the validity. Let's say I wanted to know what this valuation was, P or Q, right? And I told you that V of P is equal to 0 and V of Q is equal to 1. What would you say the valuation of P or Q is? Hopefully you would say 1, because we know from what we've done before that true or false would be true. So these same rules kind of apply. So I'm not going to go through every interpretation of conditionals and biconditionals and conjunctions. It's all the same stuff we've been doing, just with numbers now. So now that I've established these definitions, you might be like, okay, well, why did he do that? When is this going to be important? You'll see we're about to build upon it, because now what I want to do is do a countermodel. So what exactly is a countermodel? Basically, we're going to have a set of premises and a conclusion. We're going to negate the conclusion, and we're going to build a tree as normal. Now, the one I'm going to build will not close. There will be open branches, and then we're going to and as we know, if there's an open branch, then our argument is invalid. To show it's invalid, we will assign valuations, as we just did with ones and zeros, to every parameter in question that shows up in our conclusion or premises, and we will show from the valuations through a branch that our premises will be true and the conclusion will be false. And remember, if our premises are true and the conclusion is false, then our argument is invalid. So let's do that real quick. Let me make some space for us. And our premises will be, we have a lot. Well, not a lot of premises, but a lot to unpack within these premises. So we'll negate P and not Q, P and not Q, or R. Then we'll have if P, then R if and only if S. So as you can see, there's already a lot to unpack. And then our conclusion will be P if and only if Q. And remember, since this is a tree, we are negating it. So this is my argument. I'm going to write it to the side. I guess I should write this in a different color. Let's go blue. Why not? My argument is we have our premises. So we have P and not Q or R. Our other premise was what? If P, then R if and only if S. We want to claim that this syntactically entails not P if and only if Q. So let's unpack our tree. Now where do I want to start? Let's start with the first premise, our disjunction, right? So let's just check this off and start branching off our tree. So we'll have not P and not Q. There you go. It's supposed to be a Q. And then we have R right here. There we go. All right, what is the next thing that we could do? Let's expand our not P and not Q. So not P and not Q is going to become not P or not Q. So this becomes not P or not Q. So there we go. We finished that. All right. Now the next thing I'll do is unpack our second premise. So our second premise is going to become not P or R if and only if S. And I have to apply that to all three branches I have already made. So let's do that. So we're going to have not P, and then this will become R if and only if S. So there we go. And we have to put that everywhere. So not P, we have R if and only if S, and then this is going to become not P, and then we have R if and only if S. Now this is becoming a mess, and nothing has even closed yet. So what are we going to do? Oh my gosh. Yeah, well, this is a lot. So the only thing we can do now is evaluate or expand our R if and only if S's. And we can also expand our conclusion. Now, I see a way to do this quickly. So I'm going to expand our conclusion, not P if and only if Q. And I'm going to do that to the leftmost branch. So let's do that. So not P if and only if Q. That is going to be... It's going to be a lot. So not P if and only if Q. How do we... Oh my gosh. Here's what we're going to do to it. So that's going to become P and not Q. I'm pretty sure. So yeah. So it becomes P and not Q. And it also becomes or not P and Q. Now this first branch, it's going to close immediately, right? We have that contradiction. But the branch immediately to the right with our not P and Q, it hasn't closed, and there's nothing else that we can do to that branch. There's no other rule that we can apply to that branch from anywhere else. So we don't even need to finish the rest of this tree. We have a single open branch, and that's all we need to do to show that our argument is invalid. So that's why I went this way. I didn't want to fill out the whole tree. I just want to stop. So we have this branch that's open. There's nothing else we can do to it. Our argument is invalid. Now we construct a counter model. So as I said before, what we're going to do is we're going to look. So we have what letters do we have? We have P, Q, and R, right? So we want to know what the valuations of P, Q, and R are. And what we do is we look at what appears on our open branch. If the letter P, Q, or R shows up, we assign 1. If the negation shows up, then we assign 0. So on this branch, we have Q, so V of Q is equal to 1, right? We have that right here. Not P shows up. And remember, we won't have not P and P, like we won't have a parameter and its negation, because then the branch would have closed. So we have not P, so the valuation of P is 0. And then, do we have R show up at all? We don't even have R show up. Oh, and S. S is another letter we forgot. And we don't have S. So, what do we do in this situation? So, basically, what this is telling us is that, at least on this branch, since all we have are P's and Q's by themselves, no R's and S's, P being 0 and Q being 1 is all we need to know to show that this argument will lead to true premises and a false conclusion. So I can assign any valuation I want to RS. So I don't know, I'll just give them zeros, because why not? Now, if you don't believe me, after I show you how to do this like counter model, you can change the values of R and S, keep P and Q the same. You'll see that no matter what R and S are, this argument, the premises will always be true, and the conclusion will always be false. So let's draw this counter model. Now that we have valuations, what we do is we're going to plug these kind of truth values, these valuations, into our premises and our conclusion, right? And if we end up with true values, true premises, and then a false conclusion, well, this is an invalid argument, right? So let's do that. Let's rewrite it down here. Let's use, let's go yellow. So I have not P and not Q or R. My next thing is if P, then R, if and only if S. And then we have not P, if and only if Q. So let's assign our valuations. So P is a 0. Q is a 1, so not Q would be 0. 0 and 0. Remember, the 0 just means false, so 0 and 0 is 0. So we have a false thing here. Then this is negated, so this becomes true. R, 0. We have 1 or 0, so that's true or false. That's going to become a true statement. Maybe I should make my 1s look like 1s. So there we go. Our first premise is true. Now, if we put a 0 here, we know that if, with a conditional, if we have like A, if B, if A is false, it doesn't matter what B is, the entire statement will be true vacuously, right? So we know that this conditional is true. So there we go. Our second premise is true. And then for our conclusion, let's see, P is 0, Q is 1. So 0 if and only if 1, that's going to be 0. Again, false. However, this is going to end up becoming... Sorry, I totally just realized I've been writing this wrong this whole time. Let me make this yellow. I shouldn't have... I'm trying to argue, not the negation. I was trying to argue P if and only if Q, not the negation. So there you go. That doesn't change anything else. I just wrote it wrong there and there. But as you can see now, our conclusion is false while our premises are true. So that's our counter model. We have an open branch, we assign our parameters, values, 0 or 1, and then we just show when we plug those in to our premises and our conclusion, as we would with T's or F's for true or false, that will end up with true premises and a false conclusion. So, now that we have done that, that's how you do a counter model. Now, I hope you understand how to do that. But now, the question you might ask yourself when we do this tree method is, how do we know that the tree always works? How do we know that this form of arguing is good, right? Like, what even is a good argument? Here is what a good argument is. So, a good argument is sound and complete. So what does it mean to be sound, and what does it mean to be complete? Here's what I'm going to show you. Let's make some more room, and let's go back to our white color. So a sound argument, here's our definition for being sound. So if sigma, which is our set of premises, syntactically entails A, then sigma will also semantically entail A. So this is our definition of soundness. Our definition of completeness is just the opposite. If sigma semantically entails A, then sigma syntactically entails A. This is completeness. Now I'm going to give an example of real life to show like what soundness and completeness even means. Because what does that mean? All right, imagine I am a police officer, right? And my sole job is to catch people who are speeding, to catch everyone who is speeding, and only to catch people who are speeding. Then what I want is one of those, I don't know what they're called, but those guns that measure people's speed. I want a really good one of those, right? So what makes one of those speed guns good? What makes it good is a gun that goes off anytime someone is speeding and only goes off when someone is speeding. So what soundness guarantees us is that the gun will only go off when someone is speeding, meaning we'll have no false positives, right? We will only catch speedsters. However, that doesn't guarantee that we'll catch everybody, right? If I say this gun will go off only when someone's speeding, that doesn't guarantee that it'll go off every time someone is speeding. Completeness will guarantee that the gun goes off every time someone is speeding. However, that doesn't guarantee that we won't get a false positive, right? Just because it goes off every time someone's speeding, that does not mean that it won't also go off if someone isn't speeding. So soundness, completeness, they're not strong enough on their own, but if an argument is sound and complete, if my gun goes off only when people are speeding and every time someone is speeding, then I know that my gun is good. I know that my argument is good because it is sound and complete. And I am going to claim that us drawing these trees, this tableau method, is a sound and complete form of arguing, right? And let's just look up for a second. Let's go back to what we were doing. As you can see, when we did this counter model, right? And as we did in the last video, we had an open branch, so our premises did not syntactically entail our conclusion. Also, they did not semantically entail our conclusion, right? Because we found a valuation that made the premises true and the conclusion false. And if our tree, let's go back to our definitions, right? If our tree closes, right, then our premises sigma syntactically entail A, and also when our premises close, that means that there's no valuation V that makes our premises true and our conclusion false. So we know that sigma semantically entails A. So our tree method is both sound and complete. Now, I'm just speaking to you right now, right? And I just showed you an example, right? An example is not a proof. I can show you an example of a tree that is sound and complete, but that doesn't mean, and you shouldn't trust me, that doesn't mean that all trees are sound and complete, right? What I have to do is prove these to you. So that's what we're going to be doing next video. We are going to discuss the soundness and completeness lemmas. Actually, I think we might split this into videos at a time, but there's a soundness lemma, there's a completeness lemma, and then there's a soundness theorem and a completeness theorem, and we will show that the tree method is both sound and complete for those of you who are worrying maybe that this tree might not work all the time. So that was a lot to go over. I understand that it was probably tricky. That's okay. It'd be like that sometimes. But if you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.